All right, let's try to see if we can use DFS to solve a maze. Um, know that DFS need not necessarily be the best possible way to solve the maze. In fact, DFS doesn't take into account any sort of heuristics of where the end point may be, or it like will not be able to get the shortest possible path. We have several different algorithms to achieve that, but we can actually try solving a maze using DFS. It's just that it's just going to try until it succeeds. If it can succeed, that is, it's going to just try every possible way of trying to reach the end point. So let's try to see what our maze looks like. So basically, we have the starting point as the top left corner, and T is the ending point, which is the bottom right corner, and O are the obstacles. The O cell is the obstacle. It's basically a 5 cross 5 matrix, and so the only possible way to actually reach the endpoint is to just go all the way right, then go down, or then go left, then go all the way down, then again go right. So let's see if we can get our code to actually solve this using DFS. So, so on reaching a cell ij, what are our possible options? We have basically four options. We can basically go down, and what does down mean from ij? Down is just basically, so I'm calling this uh, at the starting point, which is 0 0, and I'm going to start executing a DFS at that uh, at 0 0, starting from 0 0. And what does down mean? Down is just basically I plus 1. uh, if you're at ij, down is just I plus 1. You go to the next row, and or we can go up. And what does up mean? Up is just one row above that, so it's going to be I minus 1. And or I can go to the left. And what does left mean? Left is just going to the previous column, which is j minus 1. Or I can go to the right. And what is right? Right is just j plus 1, which is to the next column. So these are my four possible steps I can take from my current cell. And I also have to ensure I stay within the maze. I don't go out of the maze. And to do that, I have here. So basically, every time I go below 0 or above 5, so so basically, 4 was our end point. So every time we go out of the boundaries, we just need to be able to stop doing that. So if it's not valid, if my current cell is not valid, I just return. And if I've stepped onto an obstacle, then also I return. If I've reached the endpoint, I celebrate, and then I return. Otherwise, if I've already visited if I've already visited the cell already, if I've already visited the cell I'm trying to visit right now, then also I return. This is pretty intuitive because like let's say I'm here, and I basically go down, and on this cell again, when you're trying to go up, you're basically repeating the same thing again, right? Like, so this could go into an infinite loop, because you're going down and then going up again, because every you're doing four possible you have four possible paths from each cell. And if you do not actually track that you've already visited a cell once, So that's why I have this visited matrix to actually track all that. So I ensure if I've already visited, I just return. I just don't try to go or try to repeat it again and again. So visited just ensures I don't go over and over the same paths again and again. This could go on and on. So to avoid doing that, I have a visited matrix, and every time I visit a cell, I mark it as visited. And let's also before going to the four paths, four directions, let's also try marking the visited cell with an X, and let's yeah, let's try marking it with an X, and let's have highlighted with green color, and let's try printing our maze at every step, and that's it. We're pretty much done. Let's see if our code runs. So I'm getting a here, and yeah, there you go. I'm getting a yes, yeah here, and I'm also printing the maze here at every function call. So, and since I've marked it with green, you can basically see what's happening. So it's starting with S, and it's going to the right, and then going two steps down, and know that at every step it has four possible directions to go, and uh, s- it's basically trying to do all that, and it's going to stumble upon O's, and it's going to have to sort of backtrack, and and this is going to go all the way till we actually can complete the maze. That is, till we stumble onto T. If we can stumble onto T, or it's going to just try to visit all possible cells. So, so it's going to the left now, and then it's going two steps down again, and then it's going all the way to the right, and it's the minute it hits T, it's going to just print yay. And I hope you can appreciate how DFS can be used to solve this maze. And DFS has a lot of applications as well. In fact, it's used in everywhere, pretty much, including like in algorithms like topological sort. Just mentioned about flood fill. Um, um, Basically, when you click a pixel, it just like it can be used to circulate to all its neighboring pixels, and then DFS is actually really useful, and it's also used in backtracking algorithms. So I hope you were able to appreciate DFS and how it can be used to actually solve the maze we just had. And note that we can use the exact same code, the exact same DFS to actually perform flood fill as well. Like, let us just remove all the obstacles and all that, the starting point, endpoints, and all that. We basically use the exact same code to basically uh, propagate, like basically circulate that green color, let's say, from 0 0 to the whole matrix. So let us try running the code. And as we can see, we start at 0 0, and then I just circulate that all the way in a depth first manner until I have the entire matrix colored with green. There you go. So that was another application of DFS, and I hope you're able to appreciate it a little better. And I'll see you in the next one.